Okay, so if you go to your Blackboard account, you're going to see the syllabus agreement. Make sure you answer it yes. Once you do, you're going to get 10 points for your test scores. So there. So that's the reason why you answer yes, to get 10 points. Not that you agree with all this stuff, but that, 10 points.
10 points is 10 points.
10 points is 10 points. That's exactly right. Okay, so if you go to labs or weekly assignments, in the weekly assignments, I'm going to start cutting pieces of either little notes that I'm going to be writing to get you to have some notes. I think that last semester one of the students gave me the feedback that sometimes might be very useful if they have some notes that they can just use, all right? So I'm going to be creating some slides for you. And so those are the slides that I'm going to be using in class. I'm not a slides guy. I really don't like them. I like to memorize stuff and then do it that way. It gives me an incredible amount of freedom to create the story I want to create. But old dogs can learn new tricks. So we're going to do it with the slides. So that way, when the thing is done, I'll give you the slides so you can have them. Okay? So you're going to have access to all the slides that we're going to be creating in class. Okay, so once you get to see the review, every week I'm going to just post, something to read, okay? After you read that and you agree that you have reviewed that, there's going to be a little button that is going to show in there for you saying that you just reviewed it. When you do that, it's going to show up with a little quiz. And the little quiz is going to be all automated, all right? You have 2 chances to answer the quiz. There's going to be 10 questions per week. You got 2 chances to answer. So you're going to go through it. The first time, whatever grade you get, when you're done, is going to show you all the questions that you got wrong. And then I'll repeat the questions again. Same questions. Right? Nothing different. Just the same questions again. So you have 2 shots. When you're done, the highest grade is going to be automatically given to you. Okay? That's the idea behind it. Now, this is all brand new, and we've been creating this hoping that it's going to help a lot of people just get instantaneous feedback. But at the same time, there's going to be some typos and there's going to be some mistakes. And if they are, please let me know right away so that I can rectify it. Okay? So that's the idea behind it. So during the week, I am going to make sure that when the reading material hits and the lecture for that particular reading material hits, I am going to be pretty much getting you ready to answer all these questions during lecture time. Okay? And so some of you are more than ready to simply read the material and go straight ahead and answer all the questions. There's no problem. But if you feel that you're not ready, just wait for the lecture. When the lecture hits, you're going to be able to answer all these questions. Okay? We're going to be running this class staggered. So we kind of worked about this last time. So if this is week 1 and week 2, and this is material for, I don't know, let's call this general purpose input-output circuits. If the lecture is given on this week, on week 1, week 1 has no lab. So this is going to be lecture, no lab. The next week, we're going to be working on interrupts. So if let's say that we're working on interrupts, I'll give you the interrupts lecture, and then in here is where you have the GPIO lab. All right, so they're staggered. So we're going to be staggering all our labs by 1 full week. Okay? So what that means is the following. The lab that I give you today, you have 7 days to work on it and then bring it back the week after. Okay? That gives you 2 choices. What I'm attempting to do with this is that if you are a student who needs help, okay, chances are that the 3 hours that we're going to spend on lab on week 2 are not going to have the students that were so capable of doing the labs that they're done. You see that? So if you take the lecture and you go like, I got this. I can do the lab all on my own. You do it during the 7 days. The classroom hits. You give me your labs. You're free to go. You don't have to stay. But if you have problems finishing your lab, I want to make sure that you get the opportunity to work with me on it. Okay? So I am very much not interested in you answering stuff in a piece of paper. I am very much interested in seeing you learning something new. whatever it takes, okay? So don't be afraid of asking or bothering me or whatever, because quite frankly, I get bored of here. So please let me know if I can be of any help, okay? So same thing next week. So if let's say that we do analog to digital conversion, here comes the lecture for that, but then the interrupts lab is going to hit a week staggered off. Does that make sense? So you're going to have weekly reading assignments, weekly online quizzes, and then weekly labs, okay? In between the semester, the labs are going to be switching from labs online that you're going to be doing on a simulator, and then every so often I'm going to make a large-scale project that will take 2 to 3 weeks to finish, okay? For example, the first one we're going to do is that we're going to take a matrix of LEDs, and we're going to learn how to take a microprocessor and then put patterns in it. How you go about creating patterns in a microprocessor. Does that make sense? So if you remember what we did in embedded, we had a one-dimensional array, and we just did a little bit of displays, and now we go 2 dimensions, and we see how do we go about creating 2 dimensions. So just one example of what we can do, okay? So that's the idea behind it. Any questions? Everything's good? All right, so let's get started. So week 1, we're going to try to get a review, okay? All right. Everybody can see? Okay, so here we go. Let's try this. Okay, the review is going to have 4 areas, okay? Which are the 4 areas that are the most important for us, especially here where we're doing microcontrollers, all right? The idea of pointers, right? The idea of pointers is what gives us access to the hardware. So that's why we're going to be doing pointers, okay? The second one is the concept of bit masking. And the idea of bit masking is the idea of gaining access to single pins inside of the processor. A pointer gives me access to large-scale circuits. Bit masking gives me access to small-scale circuits. So we're going to be studying this too. Then we're going to be working with structures. And the reason why we want structures is because a structure is going to give me the ability to divide circuits in logical units. So if I have a set of a few little circuits that together they create one unit, structures is going to give me the ability to separate them in logical software pieces. Okay, that's the idea of structures. And then finally, we're going to be doing pointers to structures because I can have the division and still gain access to those pieces of work. That's the idea behind it. If we can actually get a working idea of these 4 guys, we have every tool we need to actually succeed in this class. What you're going to notice is that the majority of the circuits that we're going to be working with are complex circuits that we learn to work with them through their behavior. So you have a circuit that behaves in a specific way. And if I change the input slightly, it behaves in a completely different way. So what we have, we all of a sudden become mechanics. Where a mechanic can actually diagnose the behavior of a circuit or a car by its behavior. If it's behaving in a specific way, this is what's wrong with it. That's what we're going to do with these micros. We're going to learn how the circuit behaves in normal conditions, and then, based on that, we can become very good at designing and troubleshooting. That's the idea behind it. Okay? All right, so, making pointers. Let me make sure that this is right. Okay, so a pointer, by definition, is a variable, okay? And these definitions, I quite frankly, we bring these definitions because this is part of what we all do as teachers, right? We love to put definitions and this and that. At the end of the day, I want to make sure that you have a mechanical understanding of how to use these pointers, okay? But in general terms, a pointer is a variable whose content is an address. In our case, for this class in particular, a pointer will contain the address of a circuit, okay? And those circuits we're going to call registers, okay? So every time you hear the word register, I want you to think in your mind a circuit, okay? We're looking at a circuit. Okay? Now, there is three things you can do to a pointer. You can make it, you can point it, and then you can use it. And you have to follow this sequence. Make sure that the sequence is not taken out of order. You have making of the pointer, the connection of the pointer, and then the using of the pointer. Okay? So they go in these three ways. So, the first one, and this is nothing more than a transition that we're trying to make. All right? So I'm trying to take you from what we learn in embedded to what we're going to be using here in micro. So as we're going along in this journey, make sure that if you find something odd, just stop me, because what it's going to happen is that you're going to notice that from the world of embedded that we went through last semester, you quite truthfully need about 20% of that to really be successful in this class. You don't need much more than that, probably even less. So the word is don't panic. This is actually quite simple, okay? So here we go. How do you make a pointer? So a pointer is made in 3 steps. You put your data type, you put the pointer operator, and then you give me a name. Those names come in 2 forms. The lowercase names is what we call general purpose pointers. These are the pointers that are used to gain access to another variable. Yes?
Is the uppercase supposed to be PTR?
It is. Thank you so much. Talking about having typos. Thank you. But yes, it should be PTR. But this guy, we call them PERT. I have no idea what that means, but it made sense when I was doing this. Okay, so the idea is behind it is that every time you find a pointer that is all capitalized, it means that we are working with a piece of hardware. We're working with a circuit. If you create a pointer with lowercase, I'm dealing with data, information. So information versus systems, right? That's the difference between these two. Make sense? Any questions? So that's how you make a pointer. How do you connect it? Even if you do not understand what we're doing in this slide, I don't want you to panic. Why? Because this is the general purpose idea. I'm just going to give you an even simpler notion. But here is the idea. Once the pointer is created, right? Once you create the pointer, you're going to need a variable of the same data type. Okay? So, if I have something that I'm going to point to, I want to make sure that whatever I'm pointing to is of the same data type as the pointer, right? So if you have a variable of the int type, I also want to have a pointer of the int type, okay? So, when instruction number 1 is executed, int x start pointer x, what you have is that you get 2 variables that have their names and their locations, because and x implies the address of x. Okay? Is that making sense? Okay. The second instruction is when you actually connect the pointer to the variable that I want. So now you take the address of x and you send that to the pointer itself. So now the pointer contains the address of x. All right? So if you really think about it, PTR, inside of PTR is the address of x. And the address of x is the location of the variable x. Okay? Now, even though this sounds kind of weird, the reality is that even if you do not understand this step, you're going to be just fine. Because this is nothing more than an understanding on how pointers operate. That's all there is to it. The embedded form of this, or the circuitry form of this, is actually way simpler. All right, so let me show you what I mean by this. Let me just give you now how to use it. So here's the user part. If I add a brand new instruction to this, and then I have the content of the pointer equals to a value, in other words, put the value 10 into the content of the pointer, what happens is that you're putting the value of 10 in the variable x, which is the variable that I'm pointing to. You remember this? So, a pointer, when I create a pointer, every time you deal with the pointer, somebody else is actually seeing the value. It's not the pointer, but somebody else, whoever I'm pointing to. Does that make sense? Okay. So, that's cool. Now, check it out. Here is how this becomes easier. What happens if I'm going to start taking a look at these pointers in the context of circuitry? Okay? So if I start thinking about this in the content of circuitry, let me just make sure that I didn't change this too much. There you go. If I start looking at this in the content of circuitry, we got the following. Check this out. Imagine that I want to connect a pointer to a register. And we said already that a register is a circuit. Okay? All right. We kind of studied last semester a little bit of this data sheet, the 18F4520, that contains a list of all the available circuits that you can change or that you can gain access to. And so the manufacturers are so nice that they give me a whole list of every single one of those circuits that I can work with. Okay? And so the list of all these circuits is here. So if I am going to connect a register or a pointer to a register, I can first look at my table and figure out which one I want to connect. So I pick port A. Why? Because it's the first one in the list. It sounded like a great idea when I was doing this. So I thought, let's pick the first one. So we say, okay, there is a circuit that is called port A. So you say int star port A. That's creation. Okay? So when you do this, you do int star port A. All right? So this portion of it, this is creating a pointer. See that? Now, when you take a look at this page, by the way, this page is out of your data sheet. It's page 65 in your data sheet, okay? So we're going to be working with that a lot. So don't worry about it. We're going to be just looking at this page. This is going to be your best friend for the rest of the semester. To the left side, there is these 4 hexadecimal numbers and letters that you're going to see here that denotes the location in memory of that circuit. Okay? So if I want to gain software access to the circuit called port A, what we're going to do is that we're going to take the address F80 hexadecimal and we're going to connect it to it. So we go equal hexadecimal F80. All right? So a couple of things to keep in mind. Okay? This is the location of port A in the 18F4520 memory map. Okay? Make sense? And notice that we have not manipulated the circuit. We just gain access to it in my software now. So that means that in my piece of software, now I have a connection to a circuit that I can now manipulate. Does that make sense? So that's the idea behind this, okay? So if you don't remember anything else about pointers, I could care less. But if you can remember one thing, that if I want you to gain access to any one of those registers through a pointer, that's how you do it. See it? There is a huge difference between the understanding of what is a pointer and just explaining it to the world and using a pointer. See that? It doesn't matter if you do not know how the car was built, but for sure you can drive it. You could be a heck of a driver, even if you do not understand how the engine works. And that's what I want to do. I want you to just go beyond your fears of C language and to understand that what you really need is just a little bit of language, just a little bit of C. And even the idea of pointers, you just need just a little bit. The only thing that I really, really want you to remember is that if I want you to gain access to port B, you know the formula to make that happen. All right? So for example, let's try it. I'm going to connect the pointer to port B. How do you do it? So I'm going to write in here, connecting a pointer to port B. We'll do connecting a pointer to port B. Okay, so if I go to the memory map, port B is located in hexadecimal F81. All right? So, how do you write it? Anybody can guide me?
Int asterisk port B equals OX F81.
Is that correct?
Yeah.
Anybody has a different idea? Why?
When you're connecting to hardware.
Yes. Very good. Tessa, you have an A. Very good. See that? The compiler will let you go and the system will actually work, but if you're working in a place with a bunch of embedded programmers, they will scoff at it. They will snicker. You don't want them snickering at you, right? So you want to make sure that it's all caps. All right? So the next one, let's take a look at tris B. So tris B is located on F93. Anybody has any doubts on how to connect circuits through pointers? It is like really easy. We're going to make sure that if we get this wrong in a test, I'm going to take 2.5 billion points off. Billion with a B. So when I am 95 and I'm still teaching this class, your great-grandchildren will come in and I will still be taking their points off. And I will say, your grandpa did not know how to connect a pointer. So there. Make sure that you remember this. All right? Here we go. So here we go. Int tris B F 90 what? 91? 93? 93. See, you guys have way better memory than I do. Okay. Okay, so this instruction, listen to what I'm going to say. You can write this down. This instruction happens only once in your code, and it will never change. These are called setup instructions. Any setup instruction happens once. Just once. Okay? Just once. And usually these instructions, because they're set up, you can do this. These connecting instructions, you can make them global. See that? So these connections could be global. Happen once, and they may be global. You know what global means, right? It means that I can do this before main. That's what that means. So in your code, you could have something like this. When you create your code, you will have your pre-processing commands. We're going to go again with these pre-processing commands next week. But for now, I'm just going to do this. And then you can come here and put your and then your main shows up. See that? So they can appear before main. That's what makes them global. Okay? Making sense? Any doubts? You guys are experts. Okay. The using pointers part, if I'm going to be using a pointer, there's a couple of things that you have to keep in mind. One, the size of the microprocessor. Because that determines the number that I can put inside of that register. Okay? That's extremely important. The size of the microprocessor, or the number of bits the microprocessor can handle, determines how I use this function. The only reason why every time I use the pointer, there is only 8 bits associated with it. It's because my microprocessor is an 8-bit device. If my microprocessor was a 16-bit device, then every time you use the pointer, you're gonna connect a 16-bit number to it. You see that? And so when you're using a pointer, there's 2 things you need. One, the connection to the pointer must have happened at some moment in the past, right? I'm predicating that I need the pointer connection. And second, you simply use the pointer by using star, name of the pointer, equals the value that I want. That's the idea behind it. So, if there is anything you remember at this from embedded, anything is how to connect pointers and how to use pointers. And it always looks like that. No ints, a star, the name of the pointer, and a number. Okay. What's the problem with this? The problem with this is that every time you use an unmasked operation, right? What I mean by unmasked, it means that I'm taking the value and I'm sending it straight into my pointer. What's going to happen is that you are manipulating every single circuit inside of that register. Right? An unmasked operation creates a maximum amount of change inside of that register. And you already know that this register is a collection of individual circuits. It's an 8-bit processor. Therefore, every register contains 8 internal circuits. And so for every unmasked operation, you're going to get 8 changes. All right? So, sometimes that's what I want to do. But sometimes that's not what I want to do. And therefore, I need bit masking. All right? That's the only reason why we're using bit masking. Is so that I can gain access to some of these elements, but not all. Okay? So that's the idea. Any questions so far? Is it making sense? All right. So you love this table. Right? You just, every time you see this table, you get flashback. Your eyes start to twitch. And at the end of the day, it's actually a very simple little table. Please let me know if I'm going too quick. I have the tendency of using slides and flying through them. So if I'm going too quick, please let me know so that I can slow down, okay? Okay, so the idea of bit masking, if you think about it from an airplane's view, is to manipulate internal bits in a microprocessor. That's the idea behind it. And in this class, you could find yourself using bit masking quite a bit. Okay? I find myself avoiding bit masking like the plague. And the reason why I avoid bit masking is because most of the code that we do, we have to read down the road again. And bit masking do not provide an easy way to remember what was the task that we were queried to do. Okay? So that's the issue behind it. However, we cannot deny is a really, really powerful tool. Okay? All right. So you're going to see on the column, the green column in there, is the 4 things you can do to a single bit. Right? The words set, reset, toggle, and read. By the way, just from a teacher's heart to a student's heart, showing you how to take tests, the reason why we have set, reset, toggle, and read is because that's exactly how we pose problems to you. We use the English language, sometimes very poorly, in an attempt to tell you, query from you your knowledge. So look for the words set, reset, toggle, and read, because the answer to all of those are always in this table. Okay? Okay, so the gate that we're using for the set bit is the OR gate. And the shape of the instruction in C language is always like that. It shows like X equal X or mask. Well, where the value of X is just a register, it's just a circuit. All right? So we're going to be manipulating circuits. Does that make sense? So what we're going to do is that I'm going to go through kind of like the same thing we did in embedded. I'm just going to show you how set works for 1 bit. Then I'm going to show you how set works for multiple bits. Then I'm going to show you how reset works for 1 bit. Then I'm going to show you how reset works for multiple bits. And so on and so forth. I just want you to kind of like remember what this bit masking was all about. Yeah?
Could you clarify on that last column what it's supposed to tell you?
Okay. The masking bit comes in 2 forms. What I consider to be a positive masking means that when the mask has a 1 in a specific bit location, it is exposing that bit to change. When it's a negative masking, the 0 does that work. Wherever I position, remember that there are 8 circuits, and I can position 8 1s and 0s in strategic spots. When I have a positive mask, when I strategically position a 1, it will create a change in the register that I'm attempting to change. In the negative mask is with the zeros. I'm going to go into a little bit more on that in just a second.
I understand a set and set, or reset. It's just a toggle and read.
The toggle is the same thing. So the toggle is x equal x exclusive or the mask, and the positive mask means that a 1 is the one that is going to force the toggle. So that's the idea behind it. And the read, if you notice the difference between the reset and the read is that there is no save operation. We're exploiting the same gate, but we're not saving the operation back into memory. So we're going to go over this one at a time, so don't panic. This table here is going to be really good for you to just like when the test comes, you can bring this to the test, so you can have this. This table tells you everything you need to know about bit masking. Okay, so let's take the set. So the bit masking concept shows up in 2 forms. Okay, it's going to show up like this: register equals register whatever operator I want, and then the mask. Right? It always shows up in that form. It never goes away from that. There is, however, a shorthand. And I have the bad habit, or this is what I learned through so many years doing firmware work, that I use the shorthand a lot. I actually get to use the shorthand because I find the code to be more compact. So, here's how the shorthand works. You have the register, what you want to do, the operator, meaning like the gate, the set, the reset, the toggle, or the read. Well, the read doesn't work this way, but the set, the reset, and the toggle, equal, and the mask. These 2 instructions are exactly the same. All right? The 2 instructions are exactly the same. So the register. What's a register? What's a register? It's a circuit. It's a circuit. There are all kinds of circuits in there, right? What is the operator? Is what I want to do. Is the task. Is the actual action. Right? The operator is the action. And the mask tells me where the action is going to happen. Right? So I have my circuit, what I want to do to the circuit, and where in the circuit I'm going to do it. That's bit masking. That's all there is to it. Okay? So here's an example. There is a circuit called IntCon. In week 3, you're going to get to know this circuit really well. It's a very interesting circuit. Inside of this circuit, there is the master switch for a whole bunch of other circuits. Circuits that control other circuits. And you have the ability to connect to it. Okay? Now, assuming that we are already connected, right? Assuming that I am already connected, that's the shape of a set instruction. See it? This is the shape of a set instruction. Okay? Okay, look at it. It goes. This is the register I want to transform. And I go, register equals register, set, location. See that? Is register equals register, operation, set, location. Okay? That's the idea behind it. Now the beauty of it is that I have a cheat sheet for you. You don't really need to remember all these things because it's actually really easy to remember. You can also bring this to the test. Every time you do your work, when I started doing this work way back when I was young, I still barely remember it. Pterodactyls used to fly. I remember those too. I used to have these little things that I carry with me because it makes my life 1,000 times easier. As time went by, if you use it long enough, you start remembering in the top of your head. Not because I sat down and like, this is the position, this is the position. It's because if you practice with it long enough, eventually you'll remember it. You have no choice but to remember it. So don't feel too much pressure. I will never ask you to remember from the top of your head, okay? So a couple of things. We have to agree on bit naming. Every register has 8 circuits. So what we're going to do is that we're going to name the circuits with numbers, okay? The least significant location, we're going to call bit 0, okay? Therefore, if I take an example from the data sheet, I'll just pick, there's a circuit in there called the capture and compare circuit. You learn about it. We're going to spend the whole week messing with this circuit. But this circuit has a name. That circuit is called CCPXM0 according to the data sheet. That's the name of it. And its location is bit 0. See that? The next guy, this is your least significant bit. They actually call it bit 0 down here. This is bit 1, bit 2, 3, 4, 5, 6, and 7. Just like we have in these boxes, okay? So from now on, every time I bring an example and I draw a box like that, in your mind you need to understand that I'm talking about circuits located from 0 to 7. That's it. So pretty simple idea. Let's name the circuits. We're going to name them with numbers. Okay? Good? All right. So here we go. There's a cheat sheet for you. So talking about positive bit masking. Okay, so this table is going to show you how to access the 0 bit if you're using a positive mask. If you want to access the 1 bit with a positive mask, that's the mask that you need. That's the 2 bit, that's the 3 bit, the 4th, the 5th, the 6th, and then the most significant 7th bit. All right? This little table, I carried it with me forever, and as time went by, I remember these numbers from the top of my head. All right? That's the idea with it. Okay, so let's go through the positive and negative so that you can see the difference. Okay, so if you are manipulating, so if I have the mask for bit 0, if you have a positive mask, according to the table, we have hexadecimal 1, right? I'm going to break this out in its binary components. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay? See that? So you see how the location relates? So a positive mask that is attempting to handle bit 0, if I just put the names of the bit up here, this is 0, 1, this is bit 2, 3, 4, 5, 6, and 7. Notice that I have a 1 located in position 0. See that? A 1 located in position 0. That's why we call it a positive masking. Right? Some people call it a highly asserted mask, and there's all kinds of names that they give it out there. When they taught it to me, they taught it as positive and negative, and somehow it's stuck in my head. So I'm just destroying your mind with the same idea now. I call it positive and negative. You can call it anything you want. The reality is that if you put a 1 in the position that you want, that's called a positive masking. Okay? The negative mask is hexadecimal FE. And then FE is this, FE. You see how it flips? Because the 0 is positioned in the place that I want. Okay? Masking has nothing to do with a numerical value that I want. The magnitude of the number does not matter. What matters is the position of the ones and the zeros. Okay? We're trying to find circuits. That's it. Where is the circuit? Once I find the circuit, I want to do something with that circuit. And the positive mask identifies circuits with a 1 and ignores circuits with a 0. While the negative mask identifies circuits with a 0 and ignores circuits with a 1. That's it. That's the difference between those two ideas. Very straightforward. Now, let me say something. If you want to use a negative mask, but it's very hard for you to remember the negative hexadecimal expression, you can always create it by simply taking the positive mask and inverting it. Okay? So if you invert the positive mask, this is a positive mask. It creates the negative mask. So this is a bitwise NOT. Some people call these the ones complement. Okay? It's just simply taking bit by bit and you flip the bits, right? If you do a bit by bit flip, you go from this to that. See that? So what I'm giving you is the choice. You can choose what to do. I personally use this stuff. I rarely in my own work use the NOT 1 because I'm old and I've been doing this for so long, and so I learned it the other way, and so it sticks. There's nothing wrong with you using the negation of a positive mask to create a negative mask. See that? Okay, so what I mean is the following now. This little table is what you're going to use to solve all your problems. Every bit masking problem in this class is solved with that table. All of them. Or a combination of them. Alright? So, position 0, that's the positive mask. Position 1, that's the positive mask. Position 0, that's the negative mask. Position 1, that's the negative mask. And so on and so forth. You simply just pluck it out of this table. You have the solution of the problem. Right? Alright, straightforward. Here we go. Let's do one. So here's bit setting. So let's take the first row. So, how to make something a 1? Bit setting actually implies to make a circuit a 1 or to see 5 volts. Now, I shouldn't say 5 volts because the reality is that some of these micros can run at 3.3, but you get the idea because you guys are coming out of digital 2. You know that most of those digital circuits operating 5 volts because they are TTL, right? Down the road, when we change to CMOS, they could run at 5, they could run at 3.3, they could run at 12, they could run at 18, they could run at all kinds of different voltages, depending on the technology. But for us, to just keep this nice and like steady compared to your embedded and your circuit 1 class, we're going to call this 5 volts. And 1 is a 5, right? That's the assumption we're going to make. So here's an example. Let's say I want to set bit 0 on the register called reg. All right? So the only thing I do is I go to bit 0. I know that set is using a positive mask. So I said, okay, so it is a positive mask. So I go the location, what I want to do, the set, the equal sign, and where. And that is out of this table. That's 1. So you simply take the shape, find the location, finish it. See that? You see that? Remember that this is a shorthand, right? It's kind of like a reminder for the shorthand. The straight operation looks like this. Reg equals reg or the mask. And the shorthand of this looks like location, operation, saving, mask. See that? So at the end of the day, every time that I hear the word set, you can pretty much close your eyes and know that there is only 3 pieces of information I need. I can write a sentence this big, and the only 3 words you're looking for are the word set, what to do, the big number, where to do it, and the register, the circuit you want to work on. That's it. See that? The rest of the stuff that we're talking about is context. So when you're looking at a problem in a quiz, or you're looking at a problem anywhere, just concentrate on those 3 keywords. What do you want me to do? Where you want to do it? Give me the big number. And with those 3, you're done. Because your operation, the location comes out of this table, and this operation comes out of the word set. And the register name is always given to you. Always. The register is a given. We always give you the register because I'm requesting something. Turn on the lights in 1460B, for example. I gave you the room number. I told you what I wanted. That's the same thing here. I want you to turn on or make one bit 0 in that register. And then that's the shape of your software. You see that? Here is the example on bit 1. The only thing I did is that the shape remains the same, and I took a look at where is my positive mask, and I just simply plug and played it. Right? What is the shape of the instruction to set bit 5? Okay, good. Reg or equals hex 20. See that? We look like geniuses now. Isn't it? It's a very simple idea. It's a very simple idea. So please, 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 the whole concept of week 1 is that I want you to shake away any fears of embedded programming. It's not that hard. The reason why the first semester looks so hard is because I have to teach you as much as I can from everything there is to know about Basic C. And now we just concentrate on the stuff that really matters for us. Does that make sense? Okay, good. Let's take a look at 2 bits. And here's the part that some people usually get kind of like a little bit confused. What if I want to set multiple bits, a whole bunch of them? Well, the beauty about this is that when you're using positive masking, you just have to simply put the bits that you want together. So for example, look at the wording. Look how I'm using the words. To set a bit, I have to use an OR gate. I know that, right? To set a bit, I must use an OR gate, okay? But if I have multiple mask locations, I want to set bit 0 and bit 1. And the reason why I put AND in really capital letters is because it is AND in the digital sense, in the digital circuit sense. I want to AND these 2 values, right? I want to have one bit and the other, which means an actual logical AND gate. That's what that means, okay? So here we go. Location 0, according to my table, is hex 1, which is written right here. Right? Location 1, bit 1, has a mask of 2. That's my table 2. Location 1 has a mask of 2. That's this number right here. And if you AND gate these 2, just go 1. If you OR gate these 2, you get this and that, right? You OR gate these 2 to create one and the other. In other words, I want that location and that location too. One way to think about it is, I want to make sure that all the bits that I want to see or that I want to change are represented in my resulting mask. So, this number down here is a 3. So now you have register, what you want to do, saving, that location, which is 2 locations in one. Does that make sense? You see that? Question. What if I want to set bits 7 and 0? How would you do it? Try it. Bit 7 and bit 0 of this guy called reg. Let's try it. Right? We have 2 circuits inside of one register. I want to set both of them. So you go, I have reg or equals, I need a number, right? And so bit 7 is this. According to that table, that's hexadecimal 80. And bit 0 is this. That's hexadecimal 1. Right? So I need this bit, and I need that bit. And this is hexadecimal 81. So what we have is register, set, save it here. Okay? Makes sense? A little bit. All right. How do you do 0 and 4? Try it. Just beat the guy, Reg. Just try it on your own. How do you do 7, 5, and 3? By the way, look at these things very carefully. You might see them in an exam in your near future. I kind of like can see the future. I know the guy who does the test. I'm going to take a crack at it. I'm going to go reg, set. We want 4 and 0. Right. Anybody wants to take a crack at it?
OX11.
OX11. All right. What about the next one? Who wants to take a crack at the next one? We want 7.
Wait, no, D.
We want 7, 5, and 3.
Which is 15. So.
7 is hex.
Oh, wait, yeah, I did that wrong. Okay. That's A. Yeah,
A. Somebody else? Give me the next one. A what? A and this?
Ocho.
That's very good in Spanish. All right. 8. Very good. Ocho.
Yeah, I didn't have that quite right.
But you see where this is going, right?
So.
It's about simply putting ones and zeros. So there are 3 little tables that are very useful for students when you're starting to get this idea. Is this table that takes a single hex number and explains it in binary format. Remember that I'm not looking for a numerical value. The fact that it's 10 or 9 or 80 really doesn't matter. What I'm really looking for is the location of the bits. Where is your circuit? Right? All those stories that you heard about Waldo, they were true. They were preparing you for micro. So where is Waldo? That's what I want to know. Where is the circuit? Show me the location of the circuit. That's what we're doing. Locating circuits. This number is a circuit locator. This is an action. There, I am going to set. And who's the circuit affected? That guy. Whatever that guy is located. See that? We're learning how to turn switch on and off.
That should be D8, not A8.
Is 1010.
1010.
My table is wrong because I need to fix that table. I was just checking to see if you guys were paying attention. Not that I made a mistake. I mean, how many times have I made a mistake? Do not answer that question. I do. I think that when I wake up, by the time that I brush my teeth, I already committed some mistakes. And it's just part of being an engineer. It's just part of the game. So yeah, what happened is that when I copy pasted in the wrong way, because this is 9, 9. That's 8, 9, 9. Should be 10, 11, 12, 13, 14. So there is one missing right here. So my apologies. I'll fix this and then I'll post it online. This is the best part about it. We can actually fix it, then post it. But then now it's on video. All right. But you have the idea, right? Does it make sense? Okay, good. Here, let me fix it for you. You're still thinking, so let's fix this.
I'm trying to figure out where you missed one.
Right here.
There's a double.
So you do this.
Yeah.
You go here, and you put it there, and then you go here. I miss. Yeah, this guy. Nothing has happened. Everything is good. Now we're just going to go and edit that video. And I was just going to say, no, I never made a mistake. Actually, you know, one of the best things about being an engineer is that the whole idea is to find the truth. It's not about being right. It's okay being wrong. There's nothing wrong with being wrong. And the reason why this is a great place to be when you're wrong is because you are about to learn something new. And to me, that's a beautiful thing. Being wrong is not a big deal. It's just, we're humans. You're a human. It's all right. It happens. So don't be afraid of being wrong. Be more afraid of not learning. That's scary when you're stuck.
It's wrong once you've built it and sold it already.
You know, I'll tell you a story. Here's a quick story. I should stop this so that nobody knows about it. But here's the quick story. I actually wrote a paper that was published in one of the most prestigious DSP magazines in the US. And then it published in 2003. And then I just hit the market. I got my copy. I opened it up and I was just, this is amazing. And I'm just reading it because, I don't know, it's kind of like this weird thing that you want to read your own brainchild, right? And I'm reading it, and when I get all the way back to the end, I'm looking at my set of equations and I found a mistake. This has gone through peer-reviewed for 3 years and nobody saw the mistake. And I saw it. I was so mortified by it because I'm thinking, all my DSP heroes are reading this right now and they're going, oh, a boo-boo. You know? And I'm going like, no, I got to hit first. So I wrote, if you find that paper online, you're going to see that the paper comes together with another paper. Because I wrote an errata right off the bat, and I send it out. And they published the errata right away. The funny part is that I started receiving emails from people saying, we never saw the mistake. So in some sense, it was good that I hit first before somebody goes like, I was wrong. So anyway. It was one of those moments. You will make mistakes. It's life. It happens. So don't worry about it. You just make a mistake, learn, and then that's it. You just keep learning. Okay. All right, here's resetting. Resetting is a little bit different because it's using a negative mask. Okay? It uses the AND gate and the negative mask. So it's using the second row of that table that I gave you, right? So, for example, the word reset implies to make a circuit 0 volts. Okay? Pretty straightforward. And here's a quick example. I'm always going to use bit 0 and bit 1 so that we don't start mixing and matching too much. But look at bit 0. This is what I want to do. The words reset. Tell me the location of the bit. And tell me which circuit you want to do this to. Right? And then I go circuit. And this is another, let's just fix this mistake too. There's an OR gate. It should have been an AND gate. This should be an AND gate, like so. There you go. So you're going to have your circuit, the AND gate, save, and the location. That's FE. That's based on the table, right? Bit 0 is FE. You see that? Nothing different or more difficult than the stuff that we did for set. Tell me what you want to do and the location you want to do it. The only thing you have to remember is set is a positive side of the table. Reset is a negative side of the table. So you simply just go from the negative side, negative mask, position 0, FE, so you go register and equals bit 0. See that? Bit 1 is FD, that's the position, so you go circuit, what I want to do, equals position. See that? That's it. You guys are experts. That's it. Now the question is, how are we going to use this in the context of circuitry? And the answer is pretty simple. We have a whole bunch of circuits with inputs. And every time you mess with one of the inputs, the behavior changes. So how can you change an input? I can make it a 0, or I can make it a 1. It's a digital circuit. That's it. Welcome to 60% of microcontrollers. That's it. Mechanically speaking, your ability to manipulate the circuit, all is surrounded in this idea. That's it. Set and reset. There is not much more we can do. The toggle is just icing on the cake. The toggle is quite frankly icing on the cake. Because toggle is when I'm lazy and I don't want to read it. I just want to change it. Just toggle. If you were a 1, be a 0. If you're a 0, be a 1. But in general terms, if you know how to set, you know how to toggle. You just change the operation. That's it. Right? All right. Let's take a look at this. Here is the set and the reset. Notice that it's the same idea like before. If I want to reset 0 and 1, right? 0 and 1. The mask for bit 0, according to the table, is FE. And the mask for 1 is FD. Right? So FE looks like this. 0 in this spot. FD looks like that. 0 in that spot. So I want a 0 in this spot and in that spot. See that? So my result is going to be F, C. See that?
Why is it 0C?
Because there is another type of very good Tanner.
Yeah, I was confused. I was like, wait.
Oh, I'll be confused myself. So it's F, C. That's the beauty about this. We can fix it on the fly. But it is FC, right? But you see the idea. Very straightforward. Any questions so far? Other than the typos that we have found? To my recollection, only one. 3 times. And I'm pretty sure that there is another.
Yep, that's the wrong.
Very good. Wrong. Okay, so let's try 0 and 4. we are resetting 0 and 4. So here comes the positions again. And then you can build your mask. Position 4 is this one. And position 0 is this one. And then I put 1s elsewhere. Like that? Make sense? What's this? It's going to be the circuit, what I want to do, save it. What's next?
0xEE.
This is 0xEE. Very good. Thank you, Tanner. Pretty straightforward, right? What about the next one? We got 7, 5, and 3. So 7, 5, and 3. And the rest are 1s. You see the operation itself, right? It's kind of like circuit identifying. Find me the circuit. The only part that is kind of like mental is to make sure you understand that set is a positive mask and a reset is a negative mask. If you remember that, setting the position of the zeros and the ones is fundamental stuff. Very straightforward, right? It's actually easier than ordering coffee at Starbucks. Have you ever noticed that they got the names of older coffees wrong? The small one, they call it tall, which is really big. And then the middle one, they call it, I think it's venti, which means 20 in Italian. So they got that wrong too.
Is it 20 ounces?
Yeah.
It's 16 ounces.
I know it's 16 ounces, so they don't get the ounces
Wow.
right either. So it's tall, venti, and grande. And then grande is also big in Spanish. So they got it wrong in all 3 languages. So that's what I'm saying is kind of weird. So anyway, it's easier than ordering coffee in Starbucks. Just pick your zeros and then put the rest of ones and look at the table and boom, you're done. So the second one will look like this. Reset, save, and then we go, this is 5, and this is 7. Very good. How do you feel about this? Good? This is very good. I think what you're going to notice is that all of a sudden all these kind of like hang-ups that we were having in embedded will just go away, and we're going to start kind of like moving really swiftly through this. And then we really get to have fun, to actually use micros for something really useful. Okay, here's toggle. I'm not going to spend too much time on toggle because toggle and reset are exactly the same. Everything is the same. It's a positive mask. So to toggle, it means to change the current voltage level. That's what that means. So if I have a circuit and I want to change its voltage level, I just simply go and toggle it. And the voltage level will change. Regardless of what the voltage level is, it will change. It's binary, so 1 to 0. That's all we have. Here is the bit 0 example. You have circuit, toggle, save, position based on a positive mask. If you really think about it, there is no difference between the set and the toggle other than the operation itself. Right? So if we put those two together, kind of like for you as a reminder, if you want to set bit number 0, the operation is reg set bit 0. See that? And if you want to toggle bit 0, you're going to have reg toggle save bit 0. See it? So at the end of the day, this is the only change. Okay? Nothing out of the ordinary. If we actually do this example, circuit, toggle those two bits, Mr. 1 and Mr. 0, right? You see that? But we can now fly through this kind of like a little bit faster, okay? Doing good? All right. I don't think you need to practice this. I think that you're experts by now, right? Bit 0 and bit 4. Bit 0 is in this position. Bit 4 is in that position. Positive mask gives me hex 1, 1, right? And then I just simply use the toggle bit. And then this guy, 7, 5, and 3, you have 7 and 5, that gives me 10, and 3, that gives me 8. So that's 8, 8 again. Right? Position, 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 position. Forget the actual numerical value. Okay? That's the idea behind it. Now, here comes the read, and I need to talk about the read a little bit because the read is a little bit different. Okay? You guys doing okay? You need a break? You're fine? Your silence tells me that we should just keep plowing ahead, right? Okay, so here we go. So here's the read a bit. I want you to notice that read is the only operation in bit masking that does not have a saving instruction. The equal sign is missing. You're not saving anything anywhere. So the read is something that I grab and I inspect. Then I can do something with it down the road. But for now, the whole idea is that the operation will never have an equal sign in it. So you're going to have X and your mask. And it uses a positive masking. So you pick the ones are the spots that you're going to inspect. Okay? So, for example, back to bit 0. If I want to read what's on bit 0, you're going to have reg and bit location. Now, if there is an equal sign, it better be into a variable that is not your register. It could be some other variable that you put in RAM maybe. So you create a variable, you call it X or whatever, and then you simply read a value and you can store it. Or you can read a value and use it. Right? There's all kinds of things we can do with it. But the part that I want you to really concentrate on is the fact that we can just simply read this value and just stay there. I want you to think about it again, not from mathematics. This is not math. This is actually where is my circuit and what is the voltage. Think about it from a circuit perspective. On that circuit, tell me that bit, what's in it. And this guy is going to say 5 volts, or he's going to say, I see 0 volts. That's the idea behind it. So the hex 1 is using positive masking for all these bits. So at the end of the day, if I want to read bit 1, I just say, there, read that bit. See it? Do not get confused by the math. That's usually what I tend to see when I'm grading stuff in embedded. I'm going like, oh my gosh, we're missing it. We're looking at this mathematically. It has nothing to do with math. Well, the explanation does, but what I'm trying to do has nothing math. It's just, here's the circuit, here's what I want you to do, here's the place I want you to do it. All right? Good? All right, here's the part that you have to be aware of. You cannot multi-bit this part. If you notice how we did the reading of multiple bits, or the setting, resetting, and toggling of multiple bits, you cannot use the same application for this. The reason for it is that there are multiple answers to the question that you're asking. For example, let's say I want to read bit 0 and bit 1 at the same time. One instruction, read both circuits. If you do that, I will do as before. I will take position 1, position 0 and position 1, and together they create position 3, which is a 1 in this spot and a 1 in that spot. Right? You see that, right? You see how these 3 is the combination of position 0 and position 1. We see that. Okay, now check this out. When you do this operation, you're going in that circuit, read those 2 bits. There are 4 possible results. Right? So you could have the result 0, 0. In other words, this operation responds with 0, 0, which means both bits are 0. And what I mean by both bits, I mean bit 0 and bit 1. The circuit in this position and the circuit in that position are both showing 0 volts. So when you do this operation, if it results in a 0, it's because both bits are 0. But it could result in a 1. If it results in a 1, it means that bit 0 is 1 only. And bit 1 is 0. See that? So, let me just write this down just to make sure that we can see this. So we're considering this operation. Read these 2 bits. Okay? So that tells me if I'm inspecting the world of these circuits, okay? So this operation is really going to do this. This and 3 is going to simply block this out. This get masked. And I'm going to be looking at this bit, and I'm going to be looking at that bit. And I'm going to try to figure out what's there. Okay? What can happen is that you could have both 0. You could have this guy being 5 volts. You could have this guy being 5 volts, but not that. And you could have both of them being 5 volts. You see what I'm saying? What I'm trying to say is the following. When you read multiple bits, you need to have in your mind the reality that you're going to have multiple answers to the question that you're asking. The answer is not binary anymore. It's not just yay, nay. When I read 1 bit, the answer is either 1 or 0, right? But when I'm having multiple bits, the answer is going to spread out as a power of 2. If I'm reading 2 bits, you're going to have 4 possible answers. If you're reading 3 bits, you're going to have 8 possible answers. If you're reading 4 bits, you're going to have 16 different answers. See that? And then you have to make sure that you handle those. Josh.
I think last semester we covered in like if statements and stuff that requires you to have a bitwise answer. That if it's 1 or
Correct.
more, or anything that's not 0, then it's yes?
Correct.
So,
Correct.
So would it count those bottom 3 as yes?
That's exactly right.
Okay.
That's exactly right. Josh is asking the question, it's a fundamental question of C language. How does C language determine what is true and what is false in a binary sense? And so when C language is using things like if statements require some sort of a question. And they're asking this question, and you are supposed to answer yes or no. What happens that if instead of giving you a question, I'll give you one of these answers, right? Instead of saying yes, no, I say 1, or I say 2, or I say 3, right? The answer is, it lies in the way that false statements are considered in C language. The number 0 is what is considered false. And true is actually defined as anything that is not false. It's defined as not false. So that means letters are true and numbers are true, and anything other than 0 is going to be considered true. So you got to be careful how you trigger this if statement. So if you're going to be messing with something like this, you can't just attempt to bypass the system. What I mean by that is this. Oftentimes you can see, kind of like we're going into a little rabbit hole, but sometimes you see this. If a register and a single number. And this if statement is actually constructed properly, because the answer to this is either numerical 0 or it's going to be numerical 1. So the only thing that this could be either true or false in a C sense, right? What Josh is asking is what happens now if I do this? If I take that register and then I end it with a 3. And now the answer to this is a little muddled, right? It's a little muddy. And the reason for it is that now I have 3 answers that are going to trigger true and only 1 answer that is going to trigger false. So this if statement is going to be capable of seeing a double 0, and it is capable of seeing any of the other 3 combinations, but I cannot tell you which one was the one who triggered me.
So it's faster than reading each one and ORing them? Because that would have the same effect, right? If you had read bit 1 and then OR it with reading bit 2.
Yes and no, I would say. I think most of the time what you tend to see is that people use a switch case for this. And so what they do is that they do something like this. They take a variable and then you make it equal to your register and hex 3, and then you take a switch and you hit it with an X, and then you go case when it is 0, you have case when it is 1, and of course you have your break here. You see what I'm saying, right? Case when it is 2, and so on and so forth. So when you're reading multiple bits, please keep in mind that if you're attempting to read multiple bits, you have multiple answers that you need to service in one way or another. It's kind of like, be aware. Down the road, we're going to have multiple buttons communicating with a microprocessor. I want to make sure that you keep in mind that if I have multiple reads, a single if statement will not do. You need more than that. Just be aware. When we get to that point, we'll help you out, okay? All right, any questions on this? Making sense a little bit? Okay, good. So, instruction that read bits 0 and 4. What does that look like? I'll get it started. So we're going to read bits 0 and bit 4. So I'll get it started. It's going to be this. What comes next? And. What's next?
But we just have it straight up because we don't have the equals.
That's right, we don't have the equals. Why we don't have the equals?
Because we're not saving it.
We're not saving it. It's a read. The read never saves, right? So we're going to have, what's next?
0x 1 1.
Very good. That's it. That's the read operation. All right? Making sense? 7, 5, and 3 is going to be A8, right? Because it's a positive mask. Same 1, 0, 1, 0, 1, 0, 0, 0. Try it. Try it in your notebook. Don't trust your teacher. Do it. I'm going downhill, guys. You are the ones coming uphill. So if you are going to read bits 7, 5, 4, and 3, 7, 5, and 3, is going to be register, read 7 and 5, and 3. Right? So this guy handles bits 7 and bits 5, and this guy is handling bit 3. The first exam is going to have a whole bunch of this. Tons of this. Right? Just to make sure that we get to use it. And then we're going to phase it out to the point that you barely are going to you're going to use this. You're going to notice that there's a sweet spot in which bit masking makes perfect sense. And there are other places where bit masking is not advisable. I want to stay away from bit masking. And then I go into pointers to structures. That's the idea behind it, okay? All right. All that stuff is great. Let's start digging into how are we going to use this for our class. Let's just do this. Pointers with a purpose. So for example, here is a circuit. It's a timer circuit, right? Microprocessors have a whole bunch of timers inside that we use for all kinds of pretty cool applications, like finding how fast something is moving in space. Like figuring out how fast a shaft of a motor is rotating so that I can tell you what are the RPMs. Like, once I know how fast this is going, I want to know how often I want to update the motor. All these things are useful when I have a timer, because I can tell time, okay? So this particular circuit is for a timer called timer 1. That's how the register is built internally, and this guy is the name of the circuit. The circuit is called T1CON, timer 1 control. That's really what it means, okay? So, using pointers, I want you to set the circuit called TMR1 on. How do you do that? Assume that the pointer is already connected. Somebody smart already connected the pointer, meaning you already know how to do it. Right? How would you set that guy? Okay? Ready? I'll get it started. I'm going to set the circuit called TMR1 on. That's the name of that circuit, okay? That circuit is inside a register called T1CON. So I go, this is where, right? That's the circuit I want to mess with, right? What do you want to do? I want to set. So then I go, set, right? Then I want to save. So you go, save it. What's the position? TMR1 on is located in bit what? Bit 0. It's on bit 0. And then the number for bit 0, I already know. That's hex 1. Because that's the position of bit 0 according to the table. Right? Make sense? All right? So if you think about it, I'm going to just now give you context to this. Here's the context. This operation turns on the power switch for the timer 1 circuit. The entire module is now on. That's what that will do. See that? The actual mechanical operation requires very little knowledge. Positioning and action. The behavior of the circuit is going to change in ways that only the data sheet can tell me. And that's the trick of embedded systems. It's about where do I position the action and the ones and zeros to create the change or the behavior that I want out of a specific circuit. See that? Once we go away from thinking how hard programming is and we put that in the back of our heads, we can start appreciating how beautiful these circuits really are. And these circuits are, quite frankly, amazing. They are so much fun. Once you go down the firmware world, you're going to start not liking the rest of the stuff, because this is instantaneous gratification. You can get really complex systems built in a very short period of time. That's why I love about this. From the moment that I started working to the moment that we put a satellite in space, it takes less than 3 years. I mean, talking about instant gratification. We have done hitchhike experiments in less than 6 months. Microprocessor driven. That's instant gratification. You start working in January, and in July, you see your experiment running in space. I mean, it's just, I can't wait, quite frankly, to just keep working in whatever I'm doing, because it is just too much fun. It's way too much fun. All right? Okay, so there it is. Next. Here is the long form and the shorthand. See that? All right, here, I'll give you another one. What if I want you to reset, or I want you to put a 0 on that circuit? Go ahead, good. Put a 0 on that circuit. Reset it. The circuit is called TMR1CS. It's called a clock select. It's selecting the source of your clock. That's what that does. I have a timer. Who's going to feed my timer? That's what that circuit does. We're going to study a little bit more about it later on. How do I put a 0 in it? Okay? Take a look at your little tables that you wrote. And let's stick a 0 on that spot. I want to reset TMR1. I think it's T1. TMR1 CS. Reset that guy. He goes crazy and starts pointing all the way to the top of the room. Okay, ready? Here we go. It goes T1 con, and then I go reset, and then location. That guy. Right? You see that? It's all table-based. All of it is table-based. You can just simply grab those 3 little tables that I gave you, the positioning of the bits, the positive and negative masking, and the little table for bit masking, and boom, all these things you can do on your own. Back to back to back to back, okay? All right, so that's that. So here's the answer. Now there's a little note. This is just the same slide as before. I just put the answers in there. But there is a problem with this, right? So there is a big problem. The problem is this. When I look at the instruction itself, it doesn't tell me that it's messing with the circuit called TMR1CS. It really doesn't say it explicitly. If I come back after a year and a half of doing this code, and I start looking at this code one more time and I see this, I have to go and open my data sheet and try to figure out what in the holy world I was doing that day. And so it takes me a little while to read it. So this is not the best solution for this problem. There is better ways to do this. These are very useful because they're very easy to use, very easy to implement. But notice that the name of the circuit is not part of the instruction, and by doing so, you are hiding your intentions. I need to look a little bit further to understand what's happening behind the instruction. And that's why structures are so useful for us. So that's what we're going to try, right? So, here we go. Structures. Are you guys okay? You need a break? Let me know if you need a break. Let's just take a little break, guys. Let's take 10 minutes. I'm going to stop this.